Hey chat, I think it's time we should take a closer look at neutralization titrations. You've already seen a curve like this. It's called a titration curve, and it's a plot of pH versus the volume of titrant added. Knowing how a titration curve works really helps us understand the chemistry behind the titration as well as justify the usage of indicators and other things. For this video, I want to teach you how the theoretical titration curve could be generated from a particular titration reaction. If you look at this curve, there are four distinct regions in the curve in terms of pH. At the start of the reaction, if you could notice, the pH is acidic. So you can imagine that this is an acid being titrated with a base. So the more base is added, the higher the pH becomes. At the start of titration, only the acid contributes to the pH of the solution. When you add base, the base is used up by the acid in a chemical neutralization reaction. Whatever is remaining of the acid will contribute to the pH. So that's the second region. That's before equivalence point. Of course, the equivalence point, again, the point where there are equivalent amount of moles of acid and base, is this steep region. Because there is an abrupt shift in the presence of acid or base, there is a very steep change in the shape of the curve. This steep region is the equivalence point. The fourth region is beyond the equivalence point. At this region, there essentially is no more acid remaining. So all of the pH is caused by the base that is in excess. So this S-shaped curve is called a sigmoidal curve. And if you could look at the choices of indicators, we have here phenolphthalein, that's colorless to purple, and then we have here at the bottom methyl orange, that's orange to light yellow. If you could see, phenolphthalein is the appropriate indicator to use because the pH range is consistent to this steep change in pH. So in the future, if you will be asked to find an appropriate indicator for an acid-base titration, make sure to look at the titration curve, locate the steep region of the equivalence point, and find a pH indicator where it changes color within that range. Alright, at this point, let's start by really thinking about how the pH of these various regions could be obtained. Let's start by considering 10 ml of 0.01 molar sodium hydroxide titrated with 0.01 molar hydrochloric acid. Our titrant here is hydrochloric acid. Because the solution contains nothing but sodium hydroxide at the start of reaction, the pH at the start of reaction should be above 7. Again, because it is basic. So let's calculate for the pH in that region. The first region, start of titration. At the start of the titration, there really is nothing there to contribute to the pH aside from sodium hydroxide and water. In this case, the acidity or the basicity of water is negligible because we have a strong base in the system. So let's conveniently ignore water for this time. Since sodium hydroxide is a strong base, all of it will be converted into ions. Sodium ion has no activity as an acid or a base. So all we need to consider is the hydroxide anion. We know that the pH is the negative log of the hydronium ion concentration, but in this case we have the hydroxide ion concentration. We can calculate instead the pOH. Doing that in the calculator, again that's 0.01 molar. We can ignore the 10 ml because it's not necessary yet. Negative log of 0.01 is 2. The pH then is 14 minus pOH. 14 minus 2 is 12. Again, this is consistent with what I told you earlier. At the start of the titration, there should be nothing in the solution to contribute to the acidity or basicity aside from the base. So the pH should be above 7. Let's now consider 5 ml added. So and in this region, it's before the equivalence point. And let's consider 5 ml HCl added. During the course of the titration, the neutralization reaction will occur. So that's sodium hydroxide reacting with hydrochloric acid to form sodium chloride, the salt, and water. Because there are more sodium hydroxide before the equivalence point than hydrochloric acid. Hydrochloric acid is sort of a limiting reagent, meaning that at the end we have excess sodium hydroxide. Since this is a 1:1 reaction, let's consider the millimoles. The millimoles of sodium hydroxide initially should be 10 ml times 0.01. 10.00 ml 0.01000 millimole per ml. The initial moles of sodium hydroxide is 0.1 millimole. At this point, we have also added hydrochloric acid. So that's 5 ml of 0.01 millimole per ml, which should give us 0.05 millimole. Now pay attention to what happens. If we start with 0.1 millimole of sodium hydroxide, and we react it with 0.05 millimole of hydrochloric acid, at the end of the reaction, there should be excess sodium hydroxide, which is 0.1 millimole, the initial, minus the millimole that was reacted with hydrochloric acid. Because this is a 1:1 reaction, we could just immediately subtract 0.05 from 0.1. But if you're having difficulty imagining why, we could also write this as 0.05 millimoles of HCl, or hydrochloric acid, and we can use stoichiometry to convert it to sodium hydroxide. So there should be 0.05 millimole of sodium hydroxide after we add 5 ml. The pH should then be 14 minus POH, which is 14 plus log of OH concentration. It becomes plus because, again, the P function is negative log. So 14 plus log of OH. The concentration of the hydroxide anion should then be 14 plus log 0.05 millimolar all over the total final volume. Since we started with 10 ml and we added 5 ml, it should be the final volume. So this is one of the few cases where you will see that we are adding volumes. Normally, we never add volumes because we recognize that volumes aren't additive. But in this case, it's mostly water anyway, so we can assume that no interactions occur that drastically change the volume. Doing this 14 plus log of 0.05 all over 15, the pH is 11.52. For simplicity, let's all report the pH or the POH with 2 decimal places. Clearly, the pH has decreased from 12 to 11.52 since we added acid. Again, we expect a titration curve to start above 7 and then steep during the equivalence point and then finally peter off to the acidic region beyond the equivalence point.